So in this video we're going to be going over AP Chemistry chapters 1 through 7 in preparation for the midterm. And essentially throughout this video we're going to be going over various concepts from these chapters through practice problems and also explanations as well. But going into this video you want to make sure you have some chemistry like sort of fundamentals down. So we'll say chemistry fun. You want to make sure you have a good understanding of sig figs, as well as sort of unit conversion or like dimensional analysis, because these things will be important for stoichiometric calculations and various problems that we will be going over throughout this video. So the first main concept we'll be going over is known as molecular or empirical formulas. And essentially, as you know, a chemical formula is sort of the way we express a certain compound. For example, we can say carbon dioxide. We know that compound to be CO2. So essentially what a molecular formula may look like is something like C5H10, which that might be a certain compound, but the empirical formula would be the simplest form of that compound. So in order to get the empirical formula of this, we have to simplify these subscripts here. So essentially this would turn into CH5, because we know that we can take each of these subscripts here and divide them by 5 in order to make them into their simplest form. And this form right here is the empirical formula. And this form over here is known as the molecular formula. So essentially the difference between the molecular and empirical formulas are that the empirical formula is essentially a simplified version of a compound's molecular formula. Sort of building off that introduction to empirical and molecular formulas, let's look at a problem that we may see on a test. So this is sort of like a test sort of problem, and also there are other resources for all of these concepts linked in the description below in a Google Drive folder, so feel free to look through that. So essentially we're saying malic acid is an organic compound that contains 41.39% carbon, 3.47% hydrogen, and the rest is oxygen. And we're saying that 0.129 moles of malic acid has a mass of 15 grams. And the question is asking for the empirical and molecular formulas of malic acid. So essentially we know that based on the information given that malic acid is comprised of some amount of carbon, so let's say X, and then hydrogen, so some amount of hydrogen, so Y, and the rest is oxygen, so we'll do that as Z. And essentially we need to find the empirical and molecular formulas. So based on the information we know that carbon makes up 41.39% of the compound, hydrogen makes up 3.47% of the compound, and oxygen makes up the rest. So we know that there's obviously 100% of the compound. So if we add 41.39 and 3.47 together, we get 44.86. And then we can subtract that from 100 to get 55.14. So we know that the compound is 55.14% oxygen. Now, essentially what we're going to have to do here is we're going to have to find these subscripts in order to create our empirical formula. And how we're going to do that is we're going to first let's assume we have 100 grams of malic acid. So basically, if we know we have 100 grams of our compound, we know that 41.39 grams is going to be carbon, 3.47 grams is going to be hydrogen, and 55.14 grams is going to be oxygen. So all we really need to do is convert all of these to moles, and then from there we can get a ratio of our carbon to hydrogen to oxygen, and then that will eventually get us our empirical formula. So let's first start with doing a little conversion here. So we're going to convert 41.39 grams of carbon to moles. So we're going to use our dimensional analysis here to moles. And we know that the molar mass of carbon is 12.011. So 12.011 grams. So these grams will cancel out, and that will get us, let's see, so 41.39 divided by 12.011. So basically we're going to be taking 4 sig figs, so we'll say there are 3.446 moles of carbon in our 100 grams. And then we're going to do the same thing for hydrogen, so 3.47 grams of hydrogen. I'm not going to write out the dimensional analysis because I'm pretty sure everyone knows how to do that. So, and we know the molar mass of hydrogen is 1.008. So we're going to take 3.47 and divide it by 1.008. And that is going to get us 3.44 moles of hydrogen. And then this is moles of carbon. And then we're going to do oxygen. So we know 54.14 grams of oxygen. And then if we convert that to moles, we're going to be dividing by the molar mass of oxygen. So 55.14 divided by the molar mass of oxygen, which is 16. And that will get us 3.44 moles of oxygen. So now that we have these ratios, we can sort of we need to create we should take the least number and then divide all of the moles by it. So essentially we're going to see that here we're going to see 3.44 is the smallest number, so we're going to divide each of these by 3.44 to get our mole ratio here. And basically these two are going to come out to 1, so we know that the subscript for hydrogen and oxygen will be 1, and then this over here is going to come out to be also 1. So essentially we know that these numbers that we got here are essentially our subscripts for our empirical formula. So based on this, we can see that the organic compound of malic acid has a empirical formula of CHO. So that is our empirical formula. So going into the next part of the problem, we already determined that the empirical formula is CHO. And now it's asking us to determine our molecular formula. So the molecular formula is essentially, as you remember from before, like sort of the non-simplified version of this. So an example of a molecular formula that may correspond to the empirical formula of CHO may be something like C10H10O10. And that's not the answer, but that's sort of the idea we're trying to get at. And essentially, we know how we can go from here to here. All we do is simplify these subscripts here in order to go from molecular to empirical. But to go from empirical to molecular, we have to use our molar mass. So essentially, we're saying that the molar mass of our malic acid, we're given the information that 0.29 moles of malic acid weighs 15 grams. So using the ratio of, we're saying 0.129 moles is 15 for every 15 grams. Essentially what we want to do is we want to get to our molar mass of malic acid, which we know that molar mass is expressed in grams per mole. So essentially this is some amount of grams over 1 mole of our compound or element. So we want to essentially get to 1 mole is for every something amount of grams. So essentially to get to 0.129 to 1 mole, all we're going to do is divide 1 by 0.129, and that gets us 7.75. So we're essentially multiplying by 7.75 here. So we're going to do the same in order to scale up this ratio. So we're going to take 15 and multiply by 7.75, and we get 116.25 grams. So now we know that the the molar mass of malic acid is 116.25 grams for every mole. So given that information, we can essentially go from our, we know that malic acid has a molar mass of 116.25 grams. So essentially we find the molar mass of our empirical formula here, and then we can find our sort of multiplying factor to get to this molar mass. And then we essentially just take our subscripts, which are, in this case, they're just 1, 1, and 1. And then we just multiply it by whatever we're multiplying over here, that factor. So essentially, all we have to do is just determine our molar mass of this compound that we have here, CHO, which is fairly easy because we just add the molar masses of C, H, and O. So 12.011 plus 1.008 plus 16, and that gets us 29.019. And essentially what we can do is now we can take our molar mass of malic acid, 116.25, and divide it by 29.019, and that gets us about 4. So we know our multiplying factor here is 4, which means that we're going to take each of these subscripts and just multiply them by 4. So given that, we know that our molecular formula is C4H4O4 because we're just multiplying by the factor we did in order to go from our empirical formula's molar mass to the actual molar mass of malic acid. So that's essentially how you solve empirical and molecular formula problems. So one of the main concepts from chapters 1 through 4 that is most important is your ability to do stoichiometry. So here's like an example, probably MC type of question that you may see on the midterm of stoichiometry. And essentially the important part is to get the important information you need from problems like this, and to ignore sort of the other stuff. So we can see that we have our chemical equation up here, and we can see that in an empty container, 8 moles of A2 and 8 moles of B react, and it was found that 25% of B had reacted. So how many moles of Z are in the container at equilibrium? So essentially, to do a problem like this, we first need to determine our limiting reactant. So in this case, we know that we have 8 moles of A2, and we know we have 8 moles of B. And essentially what I like to do is I like to use the mole coefficient ratio in order to determine the limiting reactant. And remember, the limiting reactant is just the reactant that's going to run out the fastest, meaning the chemical reaction will stop when that reactant runs out. So how you essentially do use this strategy is, we know we have 8 moles of A2, so 8 moles of A2. And we can see that our coefficient in this equation is 1. We see that A2 has a coefficient of 1, so we're going to divide it by that. So that's equal to 8. And then we know we have 8 moles of B, 8 moles of B. And then we can divide that by the coefficient for B, which we can see is 2. So that's divided by 2. So that's equal to 4. So essentially we now know that B is our limiting reactant. So now that we know that B is our limiting reactant, we essentially can base all of our stoichiometric calculations based off of the reactant B. And we know that based on the information given that only 25% of B actually reacted. So that means that we're going to do 0.25 times 8 moles to find how much actually reacted, and that is equal to 2 moles of B. So we now know that 2 moles of B actually reacted in the reaction. So essentially where we go from here is we take our 2 moles of B, and using dimensional analysis we can find out how many moles of Z were produced, because that's what we're trying to find out in the end. We're trying to find moles of Z. And all we have to do is use our stoichiometric ratio. So we know that we're trying to get to moles of Z. So we can see that 1 mole of Z here. So we're going to say 1 mole of Z for every, and in this balanced equation, or in your balanced, make sure you balance your equations essentially before doing these calculations. This problem is a little different because it uses variables, but the same concepts sort of apply. So for every 1 mole of Z, we know that we have 2 moles of B. So over here we're going to do 2 moles of B, and the moles of B will cancel out, and then we know that based on this we have 2 times 1 divided by 2. That's going to be 1 mole of Z, and that is the answer to our question. So another big concept that is part of chapters 1 through 4 is ionic equations. And I'm not going to go into like a full explanation of ionic equations. I'm just going to do a practice problem so you can see how it's done. If you need additional resources regarding ionic equations, there's that full Google Drive folder in the description that has all sorts of review worksheets and lecture slides, etc. To help you out. But for the sake of how long this video is, I don't want the video to be too long. We're just going to go over one problem for ionic equations and show how it's done. And for ionic equations, it's really helpful if you know your polyatomic ions, the charges of ions by groups on the periodic table, as well as your solubility rules. So without further ado, let me get into this question right here. So we can see that we have lead nitrate reacting with potassium iodide, and that is going to create our potassium nitrate and lead iodide over here. So the first thing you want to do is look at the states of each of these compounds. As you can see, our lead nitrate is in aqueous form, our potassium iodide is also in aqueous form, our potassium nitrate's in aqueous form, but our lead iodide is in solid form, meaning that this is an insoluble compound, meaning that we're just going to pretty much leave it alone throughout this whole process. So the first thing we want to do is write out our complete ionic equation. So any of the compounds that are written in the AQ form mean that, or the aqueous form, mean that they can be dissolved in water, meaning they will split up into separate ions So let's first just write our complete ionic equation. So we're going to start over here with our lead nitrate. We know that lead has a 2 plus charge, so Pb2 plus 2 nitrate. So nitrate is a polyatomic, and we know it has a 1 minus charge, so minus, plus 2, and we know potassium has a 1 plus charge, plus our iodine, which we know has a 1 minus charge, so 2I minus. And then that's for our reactant side. Going to the products, we know that, again, potassium has a plus 1 charge, and then plus 2NO3, and then that's going to be minus. NO3 is a polyatomic with a minus 1 charge. As you can see, I'm distributing the coefficients to each compound or element. As you can see, I've taken this 2 coefficient and applied it to the 2 over here and the 2 over here. Just make sure you're doing that and being careful while doing these problems. Okay, so, and then also we're going to write out our lead iodide in our solid form over here. Because it is a solid, it will not split up into separate ions because it's not soluble in water. So we're going to basically just ignore this for now. So now this is known as our complete ionic equation. Now, in order to go from our complete ionic equation to our net ionic equation, we need to essentially cancel out what are called spectator ions. So any ions that are the same or have not reacted on either side, or like just ions that do not undergo change during the chemical reaction. So basically we can see that we have potassium here and potassium here on the product side and reactant side, so we're going to simply just cancel those out. We see we have nitrate here and nitrate here, so those are going to cancel as well. And let's see, yep, nothing else is canceling. So now we can write out our net ionic equation. And when you're writing out the net ionic equation, it's important to write out the states of the states of our products. So essentially this is going to become Pb, or lead 2 plus, and that's going to be in aqueous form, plus 2 iodine minus, and then that is going to go, this is also in the aqueous form, and then that is going to go to lead iodide in the solid form. So as you can see, this is our net ionic equation over here. That's sort of how you go from your complete ionic equation to your net ionic equation. And yeah, that's pretty much it for ionic equations. For some problems, there may be where they won't give you the states of your products, and you will have to use solubility, or your reactant sometimes, and you'll have to use solubility rules to determine the states of those. Usually for these problems in the products, there is always one product that is in the aqueous form. So yeah, that's it for ionic equations.
So redox reactions, which are short for oxidation reduction reactions, are sort of like a chemical seesaw in which one substance gains electrons, which is why it's a reduction since electrons are negative, and the other substance loses them, which is oxidation. So this transfer of electrons between substances is what causes the reaction, and it's key. It's a key process in chemistry that basically powers everything from like batteries to breathing. So first, I'm gonna go over a couple of key ideas, and then we'll do an example together. So oxidation numbers, they tell the degree of oxidation. It's not like a atom's charge, and oxidation numbers are just for an atom, and it's not like a compound has its own separate thing. Like each atom has an oxidation numbers. So for ions, it's the same as a charge. So for example, if I have like Ca minus or something, right? A calcium ion, it'll be a -1. If it's elemental, like just Ca, just Ca, and it's not an ion, then it's 0. Or just H, for example, that'll be 0. However, an exception is oxygen, which even in its elemental state is -2 in compounds. So oxygen by itself is it'll be elemental, right? Just 0. But in compounds, for example, H2O, since that's a compound, it'll be -2. And then it is in O2, it is -1. Each oxygen has a -1 oxidation number. Halogens are -1. So halogens are the group 17, I believe, in the periodic table. Basically the second to last group. And then hydrogen is +1, but it's -1 when bonded to a metal. And then the others you could work out, since the compounds, however, do add up to the overall charge of the of the compound. So like if you have, for example, MnO4 minus, right? Manganese ox O4 minus, which is actually what we're gonna do for example. Since we know each oxygen in its compound is -1 or -2, sorry, that means O4 will be -8, and since we have a minus, we can, since it's an ion, we know that manganese will have then an oxidation number of +7. So in fact, now that we've done this, let's get to our example. And so I'll go through each of these steps as we're going through the problem. So let's begin. So here's an example. We have formic acid along with permanganate as our product, as our reactant, sorry, and that yields, and so our products are carbon dioxide and a manganese. So first off, what we're gonna do in this redox reaction is we're gonna split it into two reactions. Actually, we have a reduction and a oxidation. So the way we do that is by looking at we assign each element here its oxidation number. So let's start with this one. This one's pretty easy, since one of the rules is that for ions it's the same as a charge, so that means we have +2 here. Cool. Now over here, another rule is that hydrogen is +1, so +1. Now we know oxygen is -2, so we have 4 -2, so that's -8. And since we have a -1 here, that means we need a negative charge. So that means this is +7, the manganese. Now over here we have 2 oxygens, and so since we have 2 oxygens, that means we're gonna have and since for O2, right, one of the exceptions for oxygen was that if it's O2, that means each oxygen is -1, so that means combined this is -2. And so since this has a charge of 0, right, since it has a charge of 0, we need to figure out what does this add up to right now. We have 1 plus something minus 2 plus 1, so that's 0. We have 1, 0, so that means this is going to be 0. Next up, similar thing here. Since we have an O2 here, that means this thing is -2. That means this is +2. So now that we've got our oxidation numbers for each, we can now figure out which is the reduction half reaction, and then which is the oxidation half reaction. So let's go with the reduction one first. So for our reduction one, it's going to be related to manganese, as manganese has an individual charge of 7 and then has a charge of 2, so it loses. Not charge, oxidation number. Has the oxidation number of 7 and then has an 1 of 2, so it loses. So that means our reduction is revolving around the manganese. Actually, I want a little bit more space, and you'll see why in a sec. That's cool. Now that we got that settled, I'm gonna go a little bit down for our oxidation reaction, and so this leaves us with formic acid as one of the as our reactant, and we're going to have carbon dioxide as a product. So now this was the first step, right? Getting it into half reactions. Step 2 is to balance all elements other than oxygen and hydrogen. So let's go over here. We have manganese, that's balanced, and then that's the only other element we have that's not oxygen or hydrogen. So now, first, you want to balance out the oxygens before the hydrogens, and you'll see why in just a little bit. So you balance oxygens with H2O. We have 4 oxygens here. That means in each H2O there's 1 O. And you want 4 O's, so that means you're going to have 4 waters over right here. And now that's done. Now we're going to balance out hydrogen with H+. So that is done like this. Since we have 4 H2s, that means 8 hydrogens, we're going to have 8 hydrogens here like this. And now you can see why we did oxygen first, because with oxygen, balancing out oxygen, we add a couple of hydrogens as well. So now we want to balance the charges with electrons. So this section, for the reduction half reaction, right, we can see that over here we have a total charge of 7, since we have 8 plus 8 protons technically, and since we have plus 1 8 times, that's 8, minus 1 for the permanganate ion, we have a charge of positive 7, not a charge, an oxidation number of plus 7, and over here we have a number of just 2. So that means since this has a higher charge, we want to reduce the charge of the reactants, and so give me one sec. So we do that by adding electrons to the side which has a higher charge. Since electrons are negative, that means we're going to be reducing the charge. Since the reactants have a charge, have a greater charge by 5, we're going to add 5 electrons here. Alright, that's cool. Now, so far, we're done. Actually, for this step, I'm gonna use a different color though. But for this step, we are done. For the reduction reaction. Now we're gonna do the same thing for the oxidation reaction, and so we can see that other than oxygen, O and H, it's carbon. That's already balanced. Oxygen is balanced. Hydrogen is not balanced. So we're going to add some hydrogens over. So, and since we have 2 H's on the reactant side and 0 here, we're going to add 2 hydrogen ions, or just protons, since without an electron. It's just a proton. Now we're gonna balance the charges with electrons, which we did it in the purple. So right now we have a charge of 2 on the product side, 0 on the reactant side. We want to bring this down to 0, so we're gonna do plus 2, add 2 electrons over here. Now we're gonna multiply the reactions so that the electrons will cancel, which is what we want. So we're gonna multiply the reactant, well, the reduction half reaction will be multiplied by 2, since we have 5 and 2, right? So how do we get, we want the smallest number that we can get for both of them is 10. So we'll multiply 5 by 2 to get 10, and we'll multiply 2 by 5 to get 10. And so now we're going to be left, after multiplying, I'm going to do these 2 steps in one, but you could do it. What I'm going to do is first I'm going to multiply each reaction, right, by the number I'm going to multiply it by, and then I'm going to combine the reactants and the products. So I'm just going to do this in one step right now, really quickly. So we're left with 10 electrons plus 16 protons, 2 moles of permanganate, and then 5 moles of the fermic acid, I'll do this over here. One more space. And no, I'll do it over here. And then our products will be 2 mediums, 8 waters, 5 carbon dioxides, 10 protons on this side, and then also 10 electrons. Cool. So now what we want to do is simplify. So first, you want to make sure first thing that your electrons cancel out, and as we can see here, we have 10 electrons on the reactant side, 10 on the product side. So that means I'll use red to show them canceling it out. These cancel out. Next up, we have 16 protons over here, and we have 10 of them over here. So we can simplify this to just being 6, like this. Now, if this was in acidic conditions, then we would be done, right? It would just be 6H plus 2MnO4 minus plus 5HCOOH yields 2M and 2 plus 8 waters and then 5 carbon dioxides. However, this would be good if this was in acidic conditions. However, if it was basic conditions, then we'll have to do one more quick step. And so in that step, what we do is, actually, I'm going to write it again one more time. So, what is it? 6 plus 2M4. But what we want to do is we're going to add for each H plus that we have, we're going to add to both sides, right? So it's even. we're going to add hydroxide, which is just OH minus. H2O, and then 5 carbon dioxide. So we're going to add 6OH minus, and now look, this just becomes, this thing combined becomes 6 waters. That's pretty cool. And so now we have 6 waters. Oh, actually, no, first I'll add the 6 hydroxides over here. But now we have 6 waters on over here, and we have 8 over here, so that means we can get rid of this altogether. And then this over here, 8 minus 2 is 6, so we have 2. So if it was under basic conditions, we would be left with, I'm going to write bigger. Sometimes it just doesn't come out as good. It's HCl, which yields, which is what the arrow means, by the way, 2 magnesium, 2, just kind of looks like a Z, doesn't it? 2 waters. Oh my god. 5 carbon dioxides. And then 6 hydroxides. So if we were in basic conditions, this is what our answer would be. Oh, that's way too small. Oh well. Here's our answer in basic conditions. And if we were in acidic conditions, it would be this green stuff over here. This green stuff over here. And yeah, that's an example for the redox reaction problems. There should be more linked in the description in the Google Drive folder in the chapter 1 through 4 section. And also the notes are actually from Mrs. Barnett. So if the notes will be in the Google Drive folder, but they're also on Mrs. Barnett's Google Classroom if you do have Mrs. Barnett.
So the last concept from chapters 1 through 4 that we'll be going over is known as molarity, or molar concentration. And essentially what molarity is it is M is equal to N over L, where N is the number of moles and L is liters of solution. So essentially we can use this equation to solve problems like the one below. So let's look at this problem. Which will contain the greatest number of moles of potassium ions? 30 milliliters of 0.15 molar K2CrO4 or 25 milliliters of 0.08 molar of K3PO4. So essentially we are trying to find moles of potassium ions, using this information that is given to us. So let's first start with finding, let's first start with applying this equation to this problem over here. So for the first one, essentially what we're trying to do is we're trying to find moles of potassium. But to get moles of potassium, we're going to have to first go from moles of K2CrO4. We're going to have to go from moles of that to moles of potassium. And as we know, using this equation up here, m equals n over L, we are given m and L, which means we can essentially find n. So we are saying that our molarity for K2CrO4 is 0.15. So we're going to do molarity, and then times the liters of solution we have, which in this case 30 milliliters is just equal to, that will be 0.03 liters. 0.03 liters, and then that will be equal to number of moles. So if we take that, we'll just do 0.15 times 0.03, and then that'll get us 0.0045 moles. So 0.0045 moles of K2CR4, K2CrO4. And we're going to do the same thing with the other solution that we have, which is K3 PO4. So we know we have this will be 25 milliliters, will be 0.025 liters, and then times our molarity, which is 0.080, and then that will get us 0.025 times 0.08. That'll get us 0.0002 moles of K3 PO4. So now that we have moles of each, we can essentially just use dimensional analysis to find moles of potassium. So for this first one, we're going to work over here. We know that for every mole of K2CrO4, we have 2 moles of potassium. So essentially all we're going to do is we're going to multiply by 2 over 1. So 0.0045 will be multiplied by 2, and that will essentially give us 9 times 10 to the negative third moles of potassium in our first solution. So this will be moles K, and then we'll take this one over here, and we see for every mole of K3PO4 we have 3 moles of potassium. So we're going to multiply by 3 over 1. So 0.002 times 3 will get us 6 times 10 to the negative third. 6 times 10 to the negative third moles of K. So as we can see from our calculations, we can see that this solution of K2CrO4 gives us more moles of potassium. So essentially what we did was we used this equation over here, m equals number of moles over liters, to find our moles of, what we did was we found moles of our solution, and then from that we used our mole ratio to find our moles of potassium. So if you have any sort of other questions or concerns about this, there is that full Google Drive folder in the description that you can look through that has practice worksheets and all of those good resources.
So now we'll begin Chapter 5 of the AP Chemistry midterm review. This is gas laws. So first we'll do just a couple quick reminders. Here's a combined gas law. You want to make sure that the units for each of these are the same for the pressure, the same units volume, has the same units, and temperature has the same units. Temperature should be in Kelvin. And this is basically an example problem might be like, oh, a gas at this pressure had a volume of this at this temperature, and the pressure was increased to this, and the volume and temperature became this. What was the new pressure after the increase? If that's unknown, it might be at the something like that. And here's the ideal gas law. Well, this is pressure volume equals number of moles of the gas, that's N. R is this constant over here, so depending on the unit your pressure is at, that's what you're going to use here. And temperature is the temperature in Kelvin. And so if you're going to have, you'll have one unknown, and then you'll, after plugging in the values which will be given to you in the problem, you'll be able to solve. Ideal gases versus real gases. So ideal gases are a hypothetical substance, and they aren't real because in ideal gases they aren't affected by real world situations such as intermolecular forces. So real gases are affected by intermolecular forces, but the real gases are most similar to ideal gases when they're under high temperatures and or low pressures. So here's a practice problem. So we're given, there's a balloon. One balloon has helium and oxygen, and it says that the balloons are at the same temperature and pressure. So which gas will effuse through the balloon faster, and why? So the way you do this is look at their molar mass. That's your first step. And helium has a molar mass of 4.00 grams per mole, and oxygen gas, which is O2, has a molar mass of 16 times 2, so it's 32.00 grams per mole. So helium gas will effuse quicker since it has a smaller molar mass, meaning it is lighter, so it will be easier for it to escape and effuse. Here we have a word problem. A gaseous mixture from 16 grams of oxygen gas and 16 grams of methane gas is placed in a 10-liter flask at 25 degrees Celsius. So what is the partial pressure of the methane gas if the total pressure is 2 atm? So here's how we do this. Our first step actually should just be, first we have the mole fraction formula. So the pressure of G1, that is gas 1, so that's equivalent to X. I'll get to X in a second. Gas 1 times the total pressure. Now, X of gas 1 is equivalent to the number of moles in that gas divided by the total amount, or the total moles. So now, since there are 16 grams of O2, so let's find that first, how many moles that is, because we want to find the amount of total moles, right? So 16 grams of O2, since O2 has a molar mass of 32 grams per mole, since it's 16 times 2 grams a mole, we know that we have 0.5 moles of O2 gas. Now let's do the same thing but for the methane. gas. So methane, CH4, it has a molar mass of, or actually no, first we know that there were 16 grams of the methane, and methane has a molar mass of 16 grams. So then we get 1 mole of methane. So then we add these two numbers up, 0.5 plus, and we get 1.5 moles total. So look, that is one of the things that we wanted. Right? We want to find the amount of, because we want to go back to this, right? We want to use this for the methane gas. So let's go down. We know that there are X of, I'll do methane now. X of the CH4 equals moles of that gas. So there's 1 mole of this, of CH4 gas, divided by a total of 1.5 moles. So that we can just say 0.667. Now, we plug this X value into this equation up here, so then we get the pressure of the gas, right, is what we want to find. So that is our X value, which is 0.667, I'll just round, times the total pressure, which is 2. So then after doing this multiplication, we will get about 1.334 ATM. So that means that methane gas has a partial pressure of this, and just to and that is one of the answers on the multiple choice, on the practice multiple choice she gave. So that now we know that that's correct. Alright, now let's go back on to this one. So a gas sample is held at 1.5 ATM in a 500 milliliter flask. If that temperature is held constant and the volume is decreased to 100 milliliters, what is the new pressure? Alright. So, I don't know why it's not erasing. Let's just go over here. So this is what we're gonna use the combined gas law for this, right? Except we can just take temperature out of the equation fully, since metaphorically it isn't in this equation. We can literally take it out of the equation that we're gonna write up for this. Or if you want, we could just keep temperature at a number as like 1, but since it's gonna stay the same, and we're gonna be dividing by temperature, that's fine. We can just take it out. So we have the ideal gas, and the combined gas law, says that pressure of volume times temperature. Oh, whoops, why did I do volume 2? By the temperature is equivalent to volume 2 divided by temperature 2. Whoops. Temperature 1. But we can just take temperature out of the equation fully, since it is not, since it's constant. So now we know that the pressure is 1.5, the original pressure, 1.5 ATM, times the original volume, which is 500 milliliters. And now we set that up to be equal to the new pressure, which is P2, and that's what we want to find because it says what is the new pressure. That's this times the volume, since the new volume has decreased to 100 milliliters. And since our units are the same, milliliters, and since we have ATM over here, this means that we're gonna have our pressure answer in ATM. So now we get, I'll do one more step. We get 750 equals P2 times 100. I just took out the units, by the way. So now we get the pressure, the new pressure is 7.5 ATM after dividing by 100. And that is the correct answer. So now here, this is just a conceptual one. There's nothing to calculate. But what happens to the temperature of the gas, or what happens to the volume of the gas if the temperature in Celsius is doubled and the pressure is constant? This is also related to the combined gas law, right? So it says, yes, the pressure is constant and temperature is doubled. Temperature in Celsius is doubled. But however, since temperature is going to be in Kelvin, right? It will increase. The volume will increase, but it won't double, for example, right? Just because the temperature in Celsius is doubled doesn't mean that the temperature in Kelvin is doubled. So that means it will slightly increase, but for example, if the temperature in Celsius went from 5 degrees Celsius to 10 degrees Celsius, the pressure will increase just a little bit. However, in this example, since this is Kelvin, and we want our temperature units in gas equations to be with Kelvin, that means that the volume of the gas then will double. Welcome back now to Unit 6 of AP Chemistry Review. So we're going to go over thermochemistry in this unit. First, let's go over change in Q, or this heat gain loss equation. And so change in Q is the change in energy. It could be positive or negative, and the value is in joules. M is the mass of the object in grams. C is the specific heat capacity, which basically is the amount of joules it's required to increase 1 gram of the object by 1 degree Celsius. And change in T is the change in temperature. Enthalpy, we'll get to more of this in the practice problems that we'll do. But it's just the total heat content of the system, and it's written as change in H, or delta H, which is equivalent to Q in constant pressure. Hess's law, we'll do this more later, and so it'll make sense with the practice problems. But basically, if you flip a reaction, you have to keep in mind that you're gonna have to reverse the change in H sign. So if it's a positive to negative, negative to positive, and if the magnitude of the reaction is changed, whether it's multiplied, then you're gonna do the same thing for the change in H, or the change in enthalpy. So here's a problem. We have a 200 gram sample of an unknown metal was heated to 135 degrees Celsius. The metal was then put into a calorimeter with 100 grams of water. So the water was originally at 25 degrees Celsius, and then after the metal was put in, the temperature of the water increased to 35 degrees Celsius. And so we want to find the specific heat of the metal. And so the way we do this is we have Q, which and we set this equivalent to negative Q, because the amount of energy gained, for example, by the water is equivalent to negative the amount of energy gained, or gained, quote unquote, gained by the metal, since the metal lost energy since its temperature decreased. So since we know that Q is equivalent to MC delta T, we can say MC delta T is equivalent to negative MC delta T. So let's do the left side for water and the right side for the metal. So we said the water is 100 grams of water. We know that the specific heat capacity of water is 100 grams of water. Specific heat capacity of water is 4.18 joules per grams in degrees Celsius. And then change in temperature. So water had a temperature of 25 degrees Celsius, and then now it is 35 degrees Celsius. So that means the temperature increased by 10 degrees Celsius. So we set this equation equivalent to negative the mass of the metal, which is 200 grams, multiply that by the specific heat capacity of the metal, which is what we want to find. So let's keep that as C. And so the metal, the temperature of the metal, it was 135 degrees, then dropped down to 35. So that means so the change in temperature is negative 100 degrees in Celsius. So then we can just now plug into our calculator, use algebra, but basically C is equivalent to 100 times 4.18 times 10. Divide that by negative 200 times negative 10. So after we plug that into our calculator, we get we get 2.09. This is specific heat. It is joules per gram times degrees Celsius. And that's our answer. Cool. Now let's go on to a Hess's law problem. So we want to calculate the change in enthalpy for the following reaction given these three reactions below. So what we're going to do is, first we have this equation, right? And we have these three equations. So these are, we want to basically, first of all, you want to make this equation using these three equations, right? So we have CS2 here, carbon, sulfur. So then we have CS2 here. However, since in the reaction that we want to make, it's a reactant, but in this reaction over here, it's a product. We're gonna flip this around. So then this one will be a reactant. But since we flip this around, that means the change in H is going to be flipped around. So then that becomes negative 4. So that means and so over here, change in H equals negative 4 kilojoules a mole. Okay, now let's see, we want O2s, we need 3 O2s in our reactants. So we have O2 here and O2 here. So now do we multiply 1 by 3, do we multiply 1 by 2 and 1 by nothing? Let's think. We have, in this reaction over here, carbon plus O2 yields carbon dioxide. There's a product is carbon dioxide, and it gives us 1 mole of carbon dioxide, which is what we want in the reaction. So that means that we're not going to multiply this one by anything, since that would mess up the carbon dioxide, and this is the only carbon dioxide available. So then let's go like this. And also, you know, it's correct because we're going to write carbon here, and we have carbon right here, carbon over here. They're going to cancel out, and since carbon isn't in this equation, that means, and that's another sign that we're on the right track. So carbon plus O2 yields carbon dioxide. And so for change in H, it is positive 2 kilojoules a mole. Then we have this final equation, this middle one that we haven't used yet. And so we know that we have to multiply this by 2, so we get 3 O2s. This also makes sense because by multiplying this equation by 2, we're going to get 2 SO2s, which is what we want. So we'll multiply that one by 2, and so we'll be left with 2 plus 2 O2 yields 2 SO2. And so since we multiplied by 2, that means a change in H, the magnitude is going to be doubled, which is what's said over here. Since the magnitude of reaction is doubled, that means this, from -1, we get -1 times 2, which is just -2. So now that we think we're done, what we can do is we can multiply or we can cancel out some things first. So let's see, we have carbon here and carbon here, so we can cancel that out. And that's good because there is no carbon in the equation that we want. What else can cancel out? Okay, there's 2 moles of sulfur here, 2 moles of sulfur here. That's gone. And we know that should be gone because there is no sulfur. And that seems about it. So now let's check. So here's what our final equation we think it is. CS2 plus 3 O2, since we have 1 mole of O2 here and then 2 moles of O2 here. So that's 3 O2. So that yields, what do we say? CO2 plus 2 SO2. Alright, so now that that's exactly this one, CS2 plus 3 O2 yields carbon dioxide and 2 SO2, that means it's correct. So now we add these up, and we will be left with, we're going to be left with -4 plus 2 minus 2. So that's just -4 kilojoules a mole. Now here's another question. So it says the reaction below goes essentially to completion in a rigid insulated container, initially at 131 degrees Celsius. So now we want to see how is the temperature of the container, its contents, affected. So what would happen is the temperature of the container's contents would increase since the reaction is exothermic. Now this may seem contradictory since exothermic means a loss in energy, but since exothermic means that the energy is released, that means the container will warm up. We know it's exothermic since the change in H is negative 2220, which means that energy is released. Now, in this one, we want to calculate the change in the enthalpy formation values given to calculate the... Oh, whoops. I made a typo. But basically, we want to calculate the change in enthalpy for the reaction below given in the enthalpy formation values provided. So we know we're not even gonna have real numbers in this, right? Which sometimes you'll have. In fact, sometimes in these problems, they'll, instead of numbers, they'll just be like A, B, or C or something, because it's still the same steps you do. You might multiply A by 2, or C by -2, or something like that. So in this one, we have. Let me find a new spot. Okay. So we know we have C6H8O7, right? And that this table tells us that its specific enthalpy is V. So let's put V. Then we have 3 times sodium bicarbonate, I believe. So that means we have 3 times W. Then we have H2O, and it says H2O is X, and then it's only 1. That means we're just going to multiply it by 1. Then we say that this yields this thing, which is just Y. We have 3H2O, which this table tells us is X. Whoops. Plus 3X. And then 3CO2, which is 3 times Z. So now for the change in enthalpy, since this is what our products we want to see, we're going to subtract the product side. No, we're going to subtract the reactant side from the product side. So then, after doing the subtraction, we'll get Y, since there's no Y on this side. We'll get Y, and then we get 2X, since we have X here, 3X here. So if we subtract an X, we'll be left with 2X. Then we'll get 3Z, because we have 3Z right here. Then we have minus V, because there's nothing to get, cancel out of V. And then it'll be minus 3W. And so then this will be our final answer. And that's it for chapter 6. Thanks for watching. Alright, let's wrap up the video with a review of chapter 7, which included a lot of different topics, but some of them were atomic structure and periodic trends. So one of the topics that it included was electromagnetic radiation. We had the equation C equals lambda nu. C is the speed of light, which is about 2.998 times 10 to the 8th meters per second. We have lambda, which is the wavelength, and that's the distance between 2 peaks in the graph. And the frequency is the number of waves per second. And that's how so if we want to find one of these, because we know C, that's always the same, and one of these will be given. Another thing to keep in mind is that energy can only be gained or lost in whole number multiples, or like energy levels. You can't be at the 2.6 energy level or something, or you can't, or your energy level can't increase by 3.4. It'll only go up or down by whole number multiples. Another thing, another equation is that the energy of a photon is equivalent to h, which is Planck's constant, this number right here, times nu, or h times the speed of light divided by lambda, since we know nu is c divided by h, or c divided by, not h, divided by lambda. electron configuration. Electron configuration is useful when we're performing photoemission spectroscopy, or you're given a photoemission spectroscopy graph, and that's using that, you were able to find which element we're looking at, and we'll go into that in this video shortly. Periodic trends is another important thing in this chapter. Just keep in mind, other than atomic radius, which increases, from going top to down and right to left, everything else, ionization energy, electron negativity, and atomic radius, electron affinity, not atomic radius, those three all increase going left to right and bottom to top. Alright, so here's a periodic table we have. Let's use this as a reference for some of the problems because it will be necessary. So, what is the electron configuration of strontium, or Sr? So, it is right here on the periodic table. And so, using this chart in our mind, because it's good to have it in our mind, we can start off. So, we know that first, over here, hydrogen and helium, those are in the 1s. Those are in the 1s portion. So we know it'll be 1s2 since it's 1 and 2. So 2 electrons go in the 1s orbital. Then we have 2s2 over here. That's where lithium and beryllium are. So 2s2. Then right here we have the 2p6 portion, since there are 6 over here and we still have a long way to go. So that means it will be all 6 of those. Then we have 3s2 right here, because this is a 3s section and there are 2. Then we have 3p6 over here. It's a 3p section and there are 6. And we're still going to keep on going. Over here, this is the the 4s, and there are 2, so 4s2. Now, however, begins the D section. So in the D section, the D block, this here from titanium to zinc, that is the 3D portion. So we're going to have 3D, and since there are 10, we're going to write 3D 10. And I'll show the final answer in a sec after we finish this up. Now we're back in the P's, and this is 4P, and there's 6, so it's 4P6. 4P6. Now we have strontium is right here, right? So now this is just going to be 5s, because we're back in the S, and this is the 5th one, so it's 5s, and since strontium is the second in this, we're going to write 5s2, and this is our final answer. However, there is a much easier way to do it. However, to do the easier way, you'll still need to know, it's an easier way to write it, a much shortened way. Another thing that we can write is we take the last noble gas, so in this case krypton, so we're going to write krypton inside of brackets, and then we're going to say, since krypton basically is 4p6 up till 4p6, then we're gonna just write 5s2. And that's it. So that means, so this is our electron configuration. Both of these work, just the bottom one's quicker. It's a lot less writing if you know. However, if you don't know, then off the top of your head, then you may have to write the whole thing, which is fine. So now, what is the highest energy sublevel for barium atom? So let's go back to our periodic table. Right here, we see barium is right here, right below strontium. So that means if we know that this is 1s, we know that this is a 5s, right? That means this one, it must be the 6s, the 6s orbital. So we know that the 6s sublevel, is the highest energy sublevel for the barium atom. Alright, so now we're going to go to periodic trends, which we're going to use with this this chart over here. So which of these atoms has the largest atomic radius of these? It's hydrogen, lithium, sodium, potassium, and rubidium. So as you can see, all of these they're all in the same group, meaning the same column, right? So that means they're all equal amount left. So that doesn't help us. However, since atomic radius also increases out while they're going down, so while we have elements all in here, atomic radius increases while we're going down, so that means out of these 5 elements, rubidium, since rubidium is right here and it's the most down out of those 5, rubidium will have the highest atomic radius, or the largest atomic radius. Now, okay, so now we're given the question that out of carbon, nitrogen, oxygen, fluorine, and neon, which of them have the highest electron affinity? So if you look back to the chart, you'll remember that electron affinity increases while you're going to the right and while going up. So all of these, however, happen to be in the same period, or the same row. However, so they're the same amount higher, right? However, they're in different groups. They're in different columns. And so the most right column out of these is neon. It's this column, which has neon, which is one of the options. So that means neon has the largest negative electron affinity out of the options given. Alright, now another question. Which of the following has the smallest first ionization energy? Ionization energy is basically the amount of energy it takes to remove the first ionization energy is the amount of energy it takes to remove the first one valence electron for the atom. So going back to the chart, ionization energy increases while you're going to the right and while going up. So out of helium, neon, argon, krypton, and xenon, they're all in the same column, or the same period, or the same group, same group. So that means that xenon, however, since it's higher over here than it is here, and xenon is the lowest, that means xenon has the smallest first ionization energy. Alright, here's one of the radiation problems. A photon was emitted from an atom and had a frequency of this. How would you calculate? So we don't actually have to do the calculations. But what we would do is, if you go back right here, it's equivalent to the Planck's constant, which is this number, times the frequency, which is given to us. So that means all we're gonna do is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. That times 4.54, because since this is the frequency, went by 4 times 10 to the 14th, and this is in 1 over seconds. So this is how we would calculate right here. how we would calculate this, but we don't actually have to calculate. It just asks how. Alright, so what element does this photoemission spectroscopy represent? So the y-axis is relative number of electrons. So we know that it's not giving us a real number. Like up top, this is just binding energy. However, we can still figure out that over here, since this is the first one, right? Because since the closer electrons are to the radius, the more energy is required to take them away. So since this is the highest energy, this means that this is the closest to the radius, or not to the radius, to the nucleus. And so that means this is the 1s2 sublevel. So that means, alright, we got 1s2. Now, we go over here, and now we have 2s2. Because this is the same amount, this means we have 2 electrons here. And the next thing after 1s2 is 2s2. Now, after that, after 1s2 is 2s2, yeah, that's what I did. Then it's 2p6. So 2p, and that makes sense. This seems, if this is 2, that means this being 6 does make sense. So 2p6. Then we go here, and then this and this seem about equal. And then after 2p6 comes 3s2. And then this is a little bit higher, right? So this one we might call 3. Seems fair to have, say, in this one over here, the 3 electrons. And after 3s2 comes 3p6. So if we're gonna go back to the periodic table, we have 1s2 right here, 2s2, 2p6, 3s2, and then 1, 2, 3, 4, oh, it should be 3p3, 3s2, and then 3p3. So that means that this element should be phosphorus. Alright, final question. So given the data, how many valence electrons does element X have? The answer for this, well, it depends, as we see, and where is the huge jump in energy required. So let's make a quick table. I'll say it gives us from 1 to 5, right? So this 3, 4, 5. So for the first one to the second one, actually this, from the first to the second, it's just estimating like 1300, right? Then second to third, we can estimate like about 900. I'm just using like easy numbers, second and third. Then third to fourth, well, now this one's a big difference, about 9,000, give or take. 9,000. And then just, so that seems like that's going to be our big one, but we can just make sure. Fourth to fifth is about 3,000. Yeah, 3,000. So from, as we can see, from 3 to 4 is the biggest. And so since ionization is the amount of energy required to remove that electron, that means this element has 3 valence electrons. Since after removing the first and second one, first, second, and third ones, it's fine, right? There's not that much energy, there's not, relatively, there's not that much energy required, since these are just 3 valence electrons hanging together. But after you get the lowest of the 3, the last shell is a full shell, and so it will require require a lot more energy for it to lose an electron, since those electrons are now closer together, and so that means that it'll be 3 valence electrons. Well, this wraps up the video. Hopefully you found this useful, and thank you for watching Project Explained.